Log on, tune in, find out. Another good idea from Cambridge.
Thank you for the introduction, and first of all I want to thank the organizers for giving me the opportunity to give this talk here. In the next few minutes I'll present you part of my PhD thesis, and this is of course joint work with Anton Arnold, my PhD advisor, and with Naufel Ben Abdallah from Toulouse and Claudia Negolescu from Marseille. And let me start with our motivation which comes from semiconductor modeling. And assume you have a semiconductor, for example a diode or a transistor, one-dimensional, and now you inject an electron in the potential which comes maybe from the device. The electron here has a prescribed energy, and well, normally the simplest model to describe the behavior of an electron is in this case given by a stationary Schrödinger equation. And here I've written it down in the unscaled version. H bar is the scaled Planck constant, m is the effective mass of the electron within the device. Well, these quantities I've already explained. In order to close the system, we of course have to use some boundary conditions, and here we use so-called inhomogeneous open boundary conditions, or something that appears as impedance boundary conditions. And due to the fact that, well, these boundary conditions here are linear and we have a linear equation, we can reformulate this system here as an initial value problem. And this will be the reason why in the following talk I'm concerning only initial value problems. Well, of course, solving only one linear ODE is not a numerical challenge today, but in application, this system here, well, I mean system now because we have to solve this equation for all energies is coupled with the Poisson problem. And well, now you see this is a nonlinear problem. For this you'll need an iterative solver, and since the right-hand side you have to compute really almost all wave functions. So you see that you need really an efficient method to solve these equations. Now, so let's see in a very simple example what happens if this epsilon, so which plays the role of the Planck constant, is really small. Here, if you use our scalar equation with quadratic potential, and you see if epsilon decreases, the solution of these equations becomes more and more oscillatory. And well, what we want, well, in application, we want to fix one grid that we can solve there the wave function for all energies. What happens if you fix only a grid without concerning the wavelengths? So here I try to solve this equation with the classical Runge-Kutta scheme, which is of fourth order in step size, and you see what happens. Well, for this red line, so the dots are the computed solution. So the origin solution is resolved quite good, but you see that there is something wrong with the blue line. And the reason for this is, or one reason, of course, is that the solution, as you see, oscillates, is highly oscillatory, and the wavelength is of order epsilon. And this Runge-Kutta method, for example, need to really resolve these oscillations, and this was not the case for the blue line. And yeah, due to this fact, our goal is now to derive a finite difference scheme which can use in some sense epsilon independent grids to solve this equation. The tools we're using for this is first an analytic pre-processing of the ODE, and then we start with discretizing, just use a series representation for linear ODE solution, and finally use special numerical methods for highly oscillatory integrals that will appear in this context. So at the end of the introduction, I should also say what exactly what problem we deal with. We want to solve this first order initial value system. Below I've written down the assumption. Of course, epsilon is a small constant. L and B should be smooth matrices. L should be real valued and diagonal. So this part here causes the high oscillations. And what's very important in this approach is that we really have to assume that the eigenvalues of this matrix L here do not cross, and that they stay away from each other. So now I've specified the problem, and we can come to the first part, to the analytic preprocessing, and it's closely related to the WKB approximation. So maybe you know that for the scalar equation from the very beginning, so the Schrödinger equation, there exists an asymptotic expansion, and here written down it in this form. And since this second order equation here can be transformed to a first order system that's fit in our problem, we simply made the ansatz to approximate a fundamental system of solutions for our ODE. Well, but just take the same ansatz, truncate it as a certain order. Well, now you simply have to replace the scalar by matrices, and this phi will be a diagonal matrix and real valued. Yes, what do next? Well, we insert this ansatz into our differential equation and compute a little bit. Then we find out that we get, we can construct really these coefficients, the matrix coefficient functions and the matrix S, such that our these functions are independent of epsilon. This is very important, such that our ansatz function solves our ODE plus small perturbation. So the perturbation is of order epsilon. And the phase function that appears here is nothing but a primitive of the diagonal matrix L. And well, if the initial conditions of the of U and double if you double coincide, then you get an error estimate, or an estimator of this form, which is proportional to epsilon to m. But unfortunately, as you know, asymptotic expansions do not have to converge, and hence we cannot expect, if epsilon is fixed, that the error here tends to 0 if n tends to infinity, and thus this ansatz itself is not a suitable numerical solution. So you have to do something else. But we can still benefit from this, because, well, we've seen before that we can write our exact solution we want is equal to our ansatz functions, which we construct, where we have plus a small perturbation. And this enables us to eliminate the leading oscillations. And how is this done? Well, we introduce a new quantity y, which is the matrix inverse of this w times u. And then if you carry out the first derivative, plug it in, and use really the properties of w, you find that this y, so this new quantity, fulfills now a differential equation with a system matrix which is of order epsilon to n. And so the quantities that appears here, well, this E epsilon is nothing but here a highly oscillatory diagonal matrix. And this epsilon is, well, so a matrix which depends on epsilon, but is smooth and independent bounded of epsilon, so it holds for its derivatives. And just to illustrate what this transformation does, let's come back to our example here. Well, first of all, you can show that this wave function psi oscillates, say, around the initial condition of order 1. So this part here is only bounded by a constant, and this is exactly so what you can observe quite good here in this picture. Independent of epsilon, let's say the amplitude here is always the same size, only of the same order. Well, on the other hand side, so if you now make the same thing for the transformed quantity, you see that the new quantity y oscillates around the initial condition now of order epsilon squared. So here explicitly put n equal to 1. So this means that this new quantity y is in some sense much smoother, because the oscillation, so we damp the amplitude of the oscillation, and hence the numerics are easier. And you observe this quite good in this picture here. This is the real part of the first component of y minus the initial condition. Well, you see, well, the function is still oscillating, and if you count with it, it oscillates here even with double frequency. But You have to scale. I think you cannot read it here. The factor is 10 to minus 4. And this fits perfectly with this estimate because here epsilon is 10 to minus 10. So this is square. So we have transformed our problem. So this was the analytic pre-processing. Now we can start to discretize everything. How we do it? Well, here we simply use a series representation of the solution of our initial condition, for our initial value problem. And well, how does it look like? Well, the unique solution of our system we want to solve is given by the sum j from 0 to infinity, epsilon to n times j, and then here appear some matrices. We call them iterated integrals, ij, and the whole matrix multiplied with the initial condition. These iterated integrals are inductively defined. Simply set the first one equal to the identity matrix on the whole interval, and the other one you get multiply your iterated integral by the system matrix and integrate it. And well, how does it help us to find the discretization? Well, in order to discretize, first let's fix a grid. And here we have h step size. And then we know that on each subinterval we have an exact series representation, just from the slide before. So that means as initial condition here we take the value at xn, and then we can write down what's the value of y at xn plus 1. And as always in numerics, if you want to discretize something, you have an infinite series, you truncate it at a certain point. And this gives us the first approximation step. And the straightforward estimates show that these iterated integrals are of order h to j. And this means that the truncation error we get is of order epsilon to n times m plus 1 times h to m plus 1. So this is something which is really small, or can be very small. Yeah, so what remains to get a full discretized scheme is to find an appropriate quadrature for these iterated integrals. And how can we do that? Well, here I've written down only the first iterated integral just to get an idea what comes up. If you write down the definition, here only one component, you get here this integral, and well, these are the oscillatory matrices which are diagonal, and if you carry out this multiplication, you find, well, that this case component is given by this product. And now if we forget about all these these indices, this term which appears as this integral is of this form. Here we integrate over a certain interval. Then, so this part here is nothing but some smooth function. So let's forget about the moment that it can depend on epsilon. And we end up also here with a highly oscillatory part. And due to our assumptions from the very beginning that the eigenvalues do not cross, we have the following, that the first derivative of this phase function here is bounded away from 0. And well, how to approximate these integrals? Of course, we're not the first one to come up with this problem. There's nice work from Iseles and Orsett. And they introduced the so-called asymptotic method, which simply is the way to derive the asymptotic properties of these integrals. This is simply done by repeated integration by parts, but this method, of course, doesn't give consistency for your ODE, because it's only first order in H. But nevertheless, it's very useful to describe the asymptotic behavior. And to overcome this problem, there's, say, an improved method, the so-called Filon type method. The idea here is also very simple, and you get a powerful tool. Simply replace f by a Hermite interpolation polynomial. And if you do it such that the derivative of f and pi coincide on the boundaries of the interval up to a certain order, you get also the features here from the asymptotic method. And additionally, you get the error estimates from the Hermite interpolation. But unfortunately for this equation, for this method, you need the exact moments, which are in general not available. But this drawback can be fixed, and there's the so-called moment-free Filon type method, which was well published by Over, a previous speaker, and well, here I've written down in small letters, which we also tried, but in a very simplified version, not in this big framework. And here the idea is as follows. Simply because of the fact that the phase function, the derivative of the phase function is bound away from 0, the inverse exists, and so you can make a change of variables in your integral. And if you define this part in front now as new function g, then you can simply apply the Fillon type method, as I shown in the slide before, for this integral. That means we replace g by a Hermite interpolation polynomial, and then this integral j prime pi is exactly computable. And the advantage now, and the good news are that you do not have to compute the inverse of phi in order to get the coefficients of pi. And well, this idea yields an asymptotically correct method, and you can get error estimates of certain order in R and S depending on your Hermite interpolation. So what we did until now is first we started with an ODE, which it's hard to tackle numerically, transformed it such that we get a system matrix of order n. Then we use simply Picard iteration, which we truncated at a certain order. Here I've written down the truncation error, and then we use the moment-free Fillon type method to approximate these iterated integrals. Well, and here you should take a little bit care of the order, of course. Well, here the order is h to n plus 1. That means we should take the same order for the quadrature of these integrals. And it turns out, because you can do the transformation such that the diagonal elements here vanishes, so that means also for the first iterated integral, you can go to higher orders in epsilon. So and here we then take epsilon to n, and this yields now for the first. And so if you insert these arrows here, you see that we get epsilon to n, and the same holds for the following summon, such that we get an asymptotically correct explicit scheme for y and a convergent estimate of this form epsilon to 2n times hm. So this is in fact how this whole procedure works. Maybe some remark, you do not only need, here you can of course use other representations, for example Magnus representation of the series, and here of course your favorite method for approximating these integrals. So let me show you, let's discuss a little bit the error. So this you've shown before, but we started of course with another equation, so we have to transform back. So on this level, this what I show you in the following example. So here everything is nice, but you have to transform back, and this is really it's a little drawback of this whole ansatz, because usually this phase function phi is given by a quadrature, and if you now transform back and carry out the error estimates, see, well, this is from the transform quantity. This is nice, but then here appears the factor h to gamma, so this is the order of the quadrature for phi over epsilon, and this this indicates that this phi is really the crucial part in this whole game. But nevertheless, if phi is exact, and this may happen in some applications, then then means this part here of the error estimate disappears, and it's possible to get an epsilon asymptotic correct scheme also for you. And this means in this case we really achieved our goal from the very beginning, that we want to construct a scheme that can use epsilon independent grids. Otherwise, you get some step size restriction in order to get an epsilon uniform estimate. Okay, so as I said, there is now a numerical example, and I took this from a paper from Lorenz, Janke, and Lubich from 2005. In this paper, they discussed differential equation or systems equation of this type, And there, in detail, they derived the so-called adiabatic midpoint rule, which is a two-step, a symmetric two-step integrator. It's error estimate uniform second-order scheme. That means the convergent errors of order 2. And there, they started with this whole method. They used, in some sense, the zeroth order WKB transformation. Because it's just a zeroth order, it was not asymptotically correct, but nevertheless, it's that a very good result that you get an epsilon independent error estimates. And I'll compare this to, well, the scheme, so our explicit one-step scheme derived with this program I've shown you before. Well, it's the first order, and then we use first order WKB approximation, and we'll see that this is asymptotically correct, and the convergence error we expect is epsilon square times h square. So here's now the plot. We see the error estimates. So, so in this double logarithmic plot, so what here on this line we have the step size, and here I've plotted the relative L1 error. That means some of the average error which occurs, and these different colors here in the stand for the solutions we make with different values of epsilon, which tend from 10 to -1 to 10 to -4. And let's start with the dashed lines above. So this is, so I implemented the scheme of Lubich in 2005, and here you see perfectly well this is really independent of epsilon, and you also observe the second order behavior. And so the solid lines below are now the error estimates from our explicit scheme, and you see well they are parallel to these lines. So here you also observe that they are second order with respect to step size. And if you have a closer look here, so the distance between these lines is a factor 100. And since, well, let's say, the distance between these epsilons is a factor 10, so you also observed very good in this scheme this behavior of epsilon squared. And what is somehow remarkable, so in this part, that even for very, very large step size here, h is equal to 1, you see that the error decreases if epsilon tends to 0. Well, this is of course not the miracle. This is due to the fact that we incorporated the asymptotic nature of the solution in this scheme. Yes, finally, I want to end my talk with some questions, of course. The first thing is what to do when the eigenvalues cross, because this was one of the essential assumptions at the very beginning. The second thing is we are concerned here with the Schrödinger equation from the very beginning. And here's the big questions: how can we deal with turning points? That means if A gets 0 at some points, how can we incorporate this in our scheme? And this is very important to couple with the evanescence in the oscillatory region in the semiconductor. And then is of course the question, can we extend these ideas to PDEs? Okay, thank you for your attention.
Questions? I have one. So if I understand right, you're basing your method on the first order WKB approximation.
Yes, for example.
And do you have any problems with caustics then?
Not yet, not in these examples. There. So because there was just one in the real line, and we are only in the oscillatory regime, so this doesn't appear yet.
Those questions?
There is a whole raft of methods going in different directions in this area. So there is Magnus. Then there is modified Magnus, which is sort of similar to that, except that it uses WKB to analyze the method, not to create the method. And then Christian, in one of his papers, I think with Marlis, for the Schrödinger equation, used Neumann expansions, which is very similar to what you're doing here. So there are many, many different methods. Probably we don't have now the time to start discussing it. That sort of are hunting for the same rabbit.
Yes, maybe.
So my proposal is solve the area equation in the interval 0, 10,000 to machine accuracy.
Okay. Yeah.
And you'll have the problem not of turning points, but of starting from completely non-asymptotic regime. It is y double prime plus xy equals 0. Right at the beginning, you start from non-oscillatory regime, starts oscillating, in which WKB tells you nothing.
Yes, exactly. And this is where this point here. We have to deal with turning points.
So it can be done with modified values.
Yeah.